So first speaker is Maria Schuld. She's a researcher in Xanadu, which is a startup in Toronto, and as well as Big Data and Informatics flagship at the University of KwaZulu-Natal in Durban, South Africa. She received her PhD in 2017 for her contribution for the intersection of quantum computing and machine learning. And she co-authored the book Supervised Learning with Quantum Computers. And she's passionate about promoting emerging technologies on the African continent. And she would talk about how to distinguish ant from bees on near-term quantum computers, which I really love. So looking forward to hear about it.
I'll talk about quantum machine learning. It will be probably a short and sweet presentation. And I'm really excited because usually I have to talk about overviews of quantum machine learning in front of audiences who don't know either quantum computing or machine learning or neither of those. But I think now I will actually talk about a research paper, so this is very nice. And the paper I want to talk about is, you find the archive reference below there, and has been written, actually the first author is Seth Lodge, you see there, and the other authors are Arusa, Josh, and Nathan from the Xanadu team. So lots of credits to them. And just to give you an idea, so I assume that most of the audience, or almost all of you, knows about quantum computing, and most of you also work more or less in quantum machine learning. Just to like orient you on our famous 4 quadrants that distinguish quantum machine learning in terms of is the data that we process quantum or classical and the algorithm. We will be in the quadrant where we have classical data, and we want to like do quantum machine learning on quantum computers on this classical data. And then also I started more and more to really think that quantum machine learning is actually 2 fields, and especially at the beginning, the field was very much dominated by what I would call good old quantum computing. Someone in a talk once asked me, like, quantum computing is so new, how can it be traditional? But it's like really the mindset of doing quantum machine learning with where the goal is to get quantum speed ups. You use like algorithms like Schuld's algorithm or HHL that we know very well to like speed up machine learning algorithms. But this talk is kind of a little bit more in the near-term quantum computing. And as most of you know, the workhorse of near-term quantum computing are variation circuits. And I think also the second talk will introduce or like talk about those a bit. The idea here of doing quantum machine learning with these variation circuits is as follows. I interpret, so what you see here is kind of like a sketch of a quantum circuit, a quantum algorithm, and I interpret this quantum algorithm as a machine learning model. That means I have to do some part of my algorithm somehow has to feed in data X, so some routine S of X. Then I can like do something, like I can apply a routine, and then in the end I measure something, I can post-process it, and as also most of you will know, the big idea here is that the optimization of my model circuit happens in a classical feedback loop. So this is like the whole principle of variation circuits. So in short, I train a quantum algorithm like a machine learning model. And something I also like only recently really realized is that this model is actually quite general. So it incorporates things like Schuld's algorithm. So think of it like that. In Schuld's algorithm, you also encode data. You encode a bit sequence or something. And you don't have a trainable circuit, but then you just apply gates and then you measure. So without the optimization loop, actually this model itself is actually as powerful as machine learning itself. And a lot of my time goes into thinking about how powerful are these models? What can we say about the generalization power? In this talk, I want to talk about this paper where we actually just basically introduce a little bit of a different approach to this variation circuit model, or how to think about it in terms of learning. And it has 3 steps. So I want to actually make 3 points here. The first point is that, so this data encoding, and those of you who know me, I speak a lot about the data encoding part. I think it's like the crucial step in a quantum algorithm. This data encoding is actually something like an embedding. So in machine learning, we know embeddings as like representing your data in some kind of space where the data gets easier to analyze. So it's also called a quantum feature map or something. So part of this has been done in other research as well, in other papers as well. But now here comes the second crucial step. Once you've done the embedding of your data, you actually can totally scrap this model circuit in the middle that you usually train, because you know what is the measurement that in terms of supervised learning distinguishes or classifies your data the best. And we now just assume that classification is our task in machine learning. And this is like quite heavy or like quite a big message, because most of quantum machine learning looks what happens in this model circuit. So we say like, you actually know what's happening here to some extent. So so the rest of the talk, I will give you the fine print of this. And the third big message here is that if we don't have to train this model circuit, then we can actually train the embedding, because the embedding is actually what now determines how good my algorithm is. So these are the 3 steps I want to talk about. And you get the executive summary in the first couple of slides. Also with the thinking that usually there's like 1 or 2 people who were just interested but don't really know about the matter so much. So I just give you some pictures at the beginning, and then the subtleties will be explained after. So the basic task is classification. So I've got like 2 types of a data set out of 2 classes of data. Here I've got images of ants and bees. And the idea is like, or the task is, I have to distinguish between those. So I have a new input. I want to know, is it an ant or bee picture? And the concept of embeddings, and so there are different terms that actually mean very similar things, but not exactly the same things. So embeddings, you could have heard about them as feature maps as well. The idea of embeddings is to make data distinguishable. And to explain what that means, let's first think of how this data looks in a very natural space or representation. And that representation can be made by like just blacking and whiting the images just for simplicity. And now I can like unfold them into vectors. And since I can't plot these very high dimensional vectors, I just take 2 features out of those vectors and plot those. And this is what I would call their natural representation. And you see that everything is very scrambled. So you haven't got a very easy way to distinguish between those 2 classes. In machine learning speech, you would say a linear model, a very simple model, can't really classify this data. And in some sense, a lot of machine learning is actually busy just like unscrambling this picture here. And once you've done that, you've solved the basic task of machine learning. And the idea of embeddings or feature maps is to represent these data points as vectors in a very high dimensional space usually, or just in a different space. And the embedding is basically doing the job of disentangling your data so that they are mapped into that space, or in the space they are represented in different groups. You can also understand this as learning a distance measure in your data. And yeah, I get back to that. Oh yeah, kind of like thought about it. So in the embedding space, your distance measure, your very simple distance measure can distinguish between those things. Meanwhile, in the original space, you need a very complex distance measure. And now there's 3 things in pictures that I said before. So first point in this picture, or in this example that I just described, I want to say that quantum computers implement these data embeddings very naturally. And you will immediately recognize that if I encode a picture, whatever way I choose to do it, if I encode it into a quantum computer in this SX routine, what I do, I basically encode it in a very high dimensional vector on my very high dimensional block sphere, for example. So I have every quantum computation, not even in quantum machine learning, gives rise to an embedding in some sense. And you can't get around that actually. So that's the beauty of it. The second thing in pictures, the second point now in pictures is we know which measurement is optimal. What does that mean? If I have now a new image and I encode it into my quantum computer, so let's say on the block sphere, it's kind of here. We know what measurement on this data I can perform to actually know if this was an ant or bee. And this measurement that is optimal is the Hellstrom measurement. And this is how the paper basically started. Maybe 2 years ago, Seth came to us and said like, you guys with your variation circuits, like, I don't understand this, like Hellstrom measurement is optimal. And then like in the remaining like 2 years up to now, or 1.5 years, we literally just try to disentangle this idea of what is optimal. And this is very subtle. And I think there's still a lot to do. It's actually not so easy, but I will tell you like kind of like what I mean by optimal basically here. But we know which measurement to take. The moment your data is embedded, actually your machine learning problem in terms of quantum theory is solved. This Hellstrom measurement is not so easy to implement. So this is another tricky issue. And then the third thing also as a summary is we can learn very good embeddings. So basically if you embed your data now using just a random routine that you have thought up, which many people do in quantum machine learning, they just say like, I encode my data using this, and then I stop thinking about the encoding and I now do the real quantum machine learning, which is training my circuit. I think this is completely the wrong picture. The moment you embed your data, this is the crucial point. All the nonlinearity of your quantum machine learning algorithm is in the embedding. But so what I want to say, if we don't know what to do in terms of the embedding, and we a lot of my time goes into trying to develop theory for this, but we don't have it yet. So, and it's really tricky. Why don't we just learn the embedding? So that's the third part. And I want to show you a couple of nice pictures. And that was actually the longest part of it. And now just a couple of more beef to it. When I say that every quantum algorithm uses embeddings, just here a couple of examples. So I said Shor's algorithm also uses embeddings. In Shor's algorithm, your input will be a bit sequence, and the SX, so this encoding or embedding circuit you would use, just flips like 2 qubits, and then you would use the basis state. And this state here, as you all know, is you can represent it by a very high dimensional vector. So this is an embedding, this is a vector representation of data in some sense. And then most of you also know amplitude embedding. What does this mean in terms of like an embedding? It means you represent an input vector as basically the amplitudes of a quantum state. And here the embedding is kind of a linear map because it doesn't do anything. Like the space of the embedding is exactly the same as the original one, maybe modular some normalization. So it's not very interesting in this sense for us. And then any other algorithm, for example, here, this is one that IBM proposed, could be understood as an embedding. So this is a very general concept. And I think, and this is a bit of an excuse, that these embedding, so this whole idea of mapping these things is not new and is not in our paper, but was actually developed like in those 2 papers beforehand. And I think this is really the key to quantum machine learning, because those quantum spaces like Hilbert spaces have a lot of properties that in machine learning, so-called reproducing kernel feature Hilbert spaces have. And a lot of machine learning theory is built on Hilbert spaces and how to map into Hilbert spaces. So this is just as at the side. Now the second point, optimal measurements. And I sit here, it's a bit tricky and I'll stay at the surface, but we can go 1 layer deeper. So when I said we know which measurement distinguishes best between 2 ensembles of quantum states, well, this is the Hellstrom measurement. This is what kind of Seth came up with and said. It's actually a bit trickier. Let me first explain or refresh you, if you had your quantum information processing 101 like many years back, then what the Hellstrom measurement actually is. Given 2 classes of the embedded data, so ensembles that are basically statistical ensembles of all the AND states and all the B states. And just to remind you, if you would now implement this state, and this, I don't know if this is actually so known, it actually took us quite a while to figure out, well, not Seth, but us as we had to implement ideas, is that this corresponds to a quantum algorithm where you randomly pick an AND picture and embed it. So the entire state of like not knowing which AND picture you picked is basically represented by these ensembles, by rho and sigma. And now if you just like take the difference between the 2 and then express it in the diagonal basis to expose the eigenvalues, a Hellstrom measurement is described by these 2 operators. So which is just like a projection on all the eigenvectors that correspond to eigenvalues that are positive and all the eigenvectors to eigenvalues that are negative. And now you just compare, you take this measurement and you compare if you like measured the AND output or the B output, so to speak. So this is kind of a classifier. We call this now the Hellstrom classifier, is applying this measurement to a new input and it will give you the answer. As a side note, obviously this way of thinking about machine learning is a bit more resource intensive than most others, because you have to construct this measurement, you have to have your training data set every single time. So you can't just do this measurement in some constant way, but you always have to load your training data in some sense. Let me jump this. This intuition, okay, Hellstrom is optimal in some sense, has already been made actually before in at least 1 paper. So there are a couple of papers that touch the topic in very different angles and are quite interesting. But this one here explicitly states it. And it's an archive paper that has, I think, never been published. It's very interesting. And if it was just that, we wouldn't have like made another paper on it. But it's actually not so easy. You can't really combine those 2 frameworks of quantum state discrimination, which is the traditional sphere of Hellstrom measurements, and quantum machining so easy. Why? For example, in the Hellstrom measurement formalism, I don't know if you ever learned it or if you remember, or the idea in what sense the Hellstrom measurement was introduced is that it's optimal in state classification in the following setting. Given an unknown state, the Hellstrom measurement, if I can only apply 1 single measurement, 1 shot, the Hellstrom measurement has the highest chance of success to give you the right answer. And this is a very different setting from our quantum classifier, because if you think of, if I go back, our quantum classifier is kind of like to estimate these expectations. And on my quantum computer, I can just like run my algorithm a lot of times and get a very good like deterministic estimate of those expectations. So the stochastic nature in which quantum state discrimination is formulated is not true in quantum machine learning. So this is the second point. And now the third one, which was what we had like ages of discussion about this paper, and which I'm very, very adamant about. Optimal in machine learning is not necessarily the same as like, the not making any errors or something like that, like stochastically speaking. But optimal in machine learning is very well defined. It means to minimize a loss, like a loss function. And since you don't know the loss function on all the data, like your expected risk or something, you have the training data. So you know exactly what you want to minimize. And unless we can show that Hellstrom actually minimizes a loss function, I'm not prepared to say Hellstrom is optimal. And so it turns out, and this is now the fine print which is in the paper if you're interested, that Hellstrom minimizes the linear loss of the classifier, probably also the quadratic loss, because lots of loss functions depend like kind of on the linear loss or can be formulated in terms of it. So indeed, if you actually do all the fine print, you can reinstate the statement, but you have to be very careful about what optimal means. And to give you an intuition is this. So let's say we have one ant picture and the embedding just happened to put it up here. Your Hellstrom measurement is kind of some kind of averaging measurement that finds like some kind of average decision boundary. So it's not a support vector machine that kind of finds the maximum margin or something. So the Hellstrom measurement would actually make a mistake here, but another measurement that would measure here, which is not the Hellstrom measurement, would be better in terms of another loss function like the accuracy, where you just count how many times have I been right. So this should be an intuition that the Hellstrom measurement is not the best measurement on all loss functions. So this is, there's a whole like interesting like range of complexities. But I come to an end now, yes. The other issue, and we spent a lot of time on that, is trying to implement a near-term version of the Hellstrom measurement. So what do I mean by implement? So if I go back again, these measurement operators, so most of you will know that a measurement is equivalent to a circuit. So you could just like say, okay, I'm implementing the Hellstrom measurement. What is the circuit so that a very simple, like a Pauli Z measurement implements actually the Hellstrom measurement. So when I talk about measurements, I also talk about circuits. So what is the circuit that implements this thing? And we tried and tried and tried and tried thousands of different versions. And we think that we found an efficient algorithm. So one that, runs in time, that's a polynomial in the number of data, but not an algorithm for a near-term quantum computer. So you still need like hundreds of copies of your data that have to be encoded at the same time. So you need hundreds of qubits. So Hellstrom is not the solution. So if you want to do this, apply this framework now in the near-term regime, you have to swap the measurements. And a very nice candidate that's very natural out of much deeper reasons that I'm actually going into now is just a simple fidelity classifier, you could call it. So the measurement observables, I mean, it looks a bit strange here to put the density matrices as measurement observables, but if you compute what comes out of here, you actually literally just do this thing here. The fidelity classifier just measures overlaps to all AND data points and overlaps to all B data points, and then says like which one is closer. So if the result is negative, it should be a B data point, the X, the new input. And this is actually like now almost again trivial because, and has been like observed in lots of other papers that you can just measure the overlap to lots of data points. And the last thing that I want to say that this fidelity classifier idea is actually very closely connected to so you could say that the distance measure connected to the fidelity classifier is the Hilbert-Schmidt norm. So it's an L2 distance. Meanwhile, the Hellstrom classifier is an L1 classifier. So you really can like start playing a lot with measurement theory and it starts getting very interesting. And now lastly, and more or less quickly, so this is kind of a no-brainer in some sense, is yeah, why don't we just like now train the embedding? And so the practical way how you train it is, well, in text speech, you could say the linear loss of the fidelity measurement. We use now fidelity because we can implement it on near-term hardware, obviously, is the negative Hilbert-Schmidt distance between the two data ensembles. But if you just write it down, you see what's happening here. What you do is you just have to make a cost function that computes the overlap of all mutual AND pictures and maximize that, or mutual B pictures, maximize that, and minimize basically, or sorry, no, maximize the overlap between the AND pictures and B pictures, but minimize the mutual overlap. What happens there is that you form tight clusters that are very far apart from each other, which makes sense, right? Then you can distinguish very well. And I want to show you like some numerical results for that. So what's going on in this very like big picture here is we just do, as usual in quantum machine learning, you have a cool idea and then you implement it with like a single dimensional data point on a single qubit or something like that. But yeah, you know, we take what we can get. So here your AND and B pictures are literally just, this is just one pixel, this is one dimensional, so blue and red are the classes. And now our variation circuits are just like sequences of our X and our Y rotations, and you train the RY rotations and your data is embedded into the RX rotations, but a couple of times you repeat this whole thing. So then you get a quantum state that represents a data sample. So this one pixel of a B picture. And now you can really like just plot this, and you can see at the beginning a random embedding where we choose these parameters randomly, just like, you know, embeds data points wherever. And now here's a very important insight that repeats what I said before. If you use this embedding here of your data, and now you apply the biggest, the nicest, the longest, the deepest quantum algorithm on this, the only thing that happens with your data is that they all get rotated, but their distance mutually will be constant. And it's very hard to, I mean, you can use post-selection, some fancy manner, but it's very hard to actually get those data points separated once it's embedded. So this is why I'm saying embedding is everything. But now you can train the embedding, and what happens is after 200 steps in this simple example, you actually have the data more or less tight and well separated. And now you can use your fidelity measurement again to classify, and you get this decision boundary on your block sphere. And then lastly, I want to close with a cool example. I think we stole the idea from Andrea Mari from a transfer learning paper, where they actually, because we thought we're speaking about ants and bees all the time, so let's just like do this. But obviously we need a classical neural network for that. And what we do, we encode the pictures in a ResNet, like pre-trained. We chop off the last layer of the ResNet and make a new layer where we convert down to 2 inputs. And all those, I think these are 1024 weights, are now trainable. And now we have a variation circuit this time with 2 qubits, and again, a lot of trainable parameters. Actually, this architecture design is also something we kind of like prototyped or tried in this paper, so it's kind of like a bit of a new idea, but yeah, these variation circuits are all the same to me, to be honest. In the end, you get an output. And now here's something interesting. So, what you do in your algorithm, and this is something, we did this in Penny Lane, and this you can do very elegantly in Penny Lane, you train the quantum parameters and the classical parameters together. And now you see that, again, we can plot it on a block sphere, but like the overlap between the data sets is very nicely distinct. So you know that you trained a very good embedding. And this is now fascinating to me because I'm working on theory where this comes up all the time. We plot here what actually the classical neural network learns to output and feed into the quantum algorithm. And you see it learns to arrange its data in a periodic manner, which makes a lot of sense because we have cosine and sine functions all over our, you know, quantum functions, like our Pauli rotations. So it actually really learned to prepare this data nicely and has already done the job. So this is not a tale of quantum is better if you add it to classical or something like that. It's literally just playing around and observing what happens. And it seems that the quantum embeddings really love these periodic structures, and you can actually explain one. Okay, if you want to do it yourself, you can see this as a demo in Penny Lane. So we try to take, Penny Lane is Xanadu's software framework for quantum machine learning. We try to take almost every paper that we really like and turn it into a code and a tutorial, so you can actually play around. Now that was enough, and yeah, I'm happy if you've got questions.
Okay, thank you, Maria. I think there is a question in the chat, and please type any other questions or just unmute yourself. So Karem El-Safti asks if about quantum embeddings, specifically, is there a quantum analog to the BC dimension of quantum kernels? For example, BC dimensions of a polynomial kernel is the degree of it plus 1. So what about the quantum embeddings?
Of the VC dimension, right? So this is exactly the stuff of research I want to see, to be honest. Like, so if we know that quantum computing is close to quantum kernels, and we know, so just for everyone else to explain, so VC dimension is a measure of a model's flexibility, and it's out of an old theory that says flexibility is actually bad, but nowadays it's a bit more shaky, this picture. But however, it tells you something about the generalization power of models. So now can't we just compute the VC dimension of quantum models and say like they can generalize or they can't generalize, which means they are good machine learning models or not. And this has to happen it is actually not so easy. If you sit down, so first of all, you have to actually define what the quantum kernel is. And the quantum kernel is, since you have to take absolute squares, if you kind of measure things, your definition of a quantum kernel is subtly strange. And then you have to go through all the theory and like compute those bounds. The second thing is that often VC dimensions are made on models like support vector machines. And I'm personally not entirely sure what type of support vector machine a quantum kernel support is or gives rise to if you use the entire quantum model. So all I want to say is I tried working on this for a while now, and it's really hard if you want to nail it down. And I'm really happy if someone publishes paper. This is the one thing I want to be scooped on because I want to see it rather than do it.
Okay, I have also a question myself. So with these embedding maps, and so you talk all the time of binary classification. So we actually tried something similar, but also expanded it to multi-classifier. But the problem was that it's more or less easy to think about the different classification of Hellstrom measurements on the qubit surface, on the block sphere surface. But when you move to multiple dimension, multiple classification, it becomes very complicated. So I have the question if you have think about how to expand it to multi-classification.
Yeah, that's, I think, very hard because state discrimination theory becomes very hard if you think about more dimensions. So basically it becomes really hard now to establish the quantum result, the quantum part of the result, to say actually that, you know, Hellstrom is the best or which measurement is the best. So I think this really works best for binary classification. And for me personally, I always think, you know, binary classification, multi-class classification, you can reduce to binary classification. So as long as you're theoretically thinking about something, it should be the same. But I hear you that in practice people want that. So no, I don't have a good answer to that.
Yeah, exactly. So I remember trying to apply and also applying the Hellstrom measurement. It's in general hard when you to find the correct measurement. So I understand that. And then if you try to generalize it to multi-class, and we tried to do that, and it was really hard and especially computationally costly. So yeah. Okay, thanks. We also have time maybe for a couple of more questions, and then if you want to wait until the end of the presentation, so we'll have more time to discuss with the speakers. So let me check. Yeah, Elias asks, I wanted to ask how this result could transfer over tensor network approaches.
Could transfer to tensor network approaches. So I think I can't answer that, but I can just say like what immediately rings a bell. So this whole idea of embeddings comes from actually the tensor network community, who, if you know, like there's a paper by Miles Staudenmayer and Schwab, that was the first time like someone had this idea that quantum encoding can actually, you know, is an inspiration. So just encoding like data into single qubit rotations, you can understand this like as a structure that like does this feature map stuff, and then you can use an MPS or like tensor network afterwards. So I think if I would try to answer this question, this would be the first paper I would look for. But otherwise, yeah, I don't know what the links were. One thing that I failed to mention is, well, this is actually a framework. I still haven't nailed down what's the important thing about this idea that I just presented. But everywhere you look, there's interesting connections. So for example, this whole framework, so I had the honor to speak to Jan LeCun recently on a conference, and I gave, you know, the presentation, and then afterwards he took time, an hour, to speak to me about it. And he said, we know this in classical machine learning, and this is called, oh gosh, I have a blackout. Can someone help me? It's like measure. Well, anyways, all the concepts are really known to classical machine learning community. And there's actually more and more work recently on this idea of like learning and embedding that separates data and then trying to classify things. So so there's lots of like different avenues that you can go. That's what I want to say. I'll tell you the word when it comes to me again. I'll look it up.
Okay, I think that we don't have more time for questions by now, but there are many interesting questions that in the chat. So please, Maria, feel free to answer them in the chat or just wait until the end of these two talks. Move to the next speaker, otherwise we're running out of time.